What's on the menu for today? Well, we now have gotten good at solving second order, linear, constant coefficient, homogeneous, no right-hand side equations. I went looking for a laser pointer this morning. Impossible to find them in any place. But fortunately I found this here, so we have this instead. It's actually much better than a laser pointer because it's got a nice red tip on the end and everything. Right? And I can whack people with, yes. Yeah. How do you solve such equations? You substitute. We recognize that if you substitute the exponential function e to the rt, where r is some constant, that each of these terms simply gives you back a polynomial times e to the rt. This gives us back qe to the rt, this pr e to the rt, and this r squared e to the rt. So if we can pick our r to satisfy this being 0, namely if the r is this, then we have a solution, because when we substitute e to the rt, we get indeed 0 for those particular values of r. Now the three different cases we looked at is when this guy, the radical, when p squared is greater than 4q, we get two real distinct roots. For instance, in example number 1 here, p squared over 4 is 4, q is 3, so we get two real roots. One of them is -1, the other is -3. So e to the minus t and e to the minus 3t are solutions. Then if p squared over 4 is equal to q, like in case 2 here, then you get just one repeated root. In that case, the solution is e to the minus 2t, and a second essentially different solution, the Wronskian between those two guys, is non-zero. So the basis, we look for a general solution as a times this and b times this. Now, the more interesting cases for many of our applications come when q is much less than, q is greater than p squared over 4, or p squared over 4 is less than q, because then we get two complex conjugate roots. Minus p over 2 plus I times the square root of q minus p squared over 4, and minus p over 2 minus I times the square root of q minus p squared over 4. In that case, in order to make real solutions out of e to the this rt and e to the this rt, we take, as I've shown you, two linear combinations to give us the cosine and the sine. For instance, in this case, when p is 2 and q is 10, the roots are -1 plus 3i and -1 minus 3i. And taking the right linear combinations just gives us the two solutions, e to the minus t cos 3t and e to the minus t sine 3t. And a linear combination of those allows you to satisfy any initial conditions, in fact at any point, because here of course p and q are constants and therefore continuous everywhere. Now what's going to be more interesting in the applications is when this p guy, this is the damping, if you remember. When we were looking at the spring, we had m times d2x by dt squared is equal to the sum of the forces. One of the forces was friction, proportional to the velocity. We call it minus b dx by dt. So this term really is the damping. Or in the LRC circuit, it's the resistance in the circuit. And in many cases of great interest, we're interested when the p is quite small compared to the q. The q, remember, in the spring system, represented the restoring force of the spring. Okay? In the LRC circuit, it represented 1 over C, 1 over the capacitance. So, in the cases where you get oscillations, of particular interest are those oscillations where the damping is rather weak compared to the wiggling, the cos 3t and the sine 3t part. And a special case of this, of course, is when the damping is 0, and now I've taken Q as 9, and then the two solutions are cos 3t and sine 3t. Because when P is 0 and Q is 9, this is r squared plus 9 is 0, r is equal to 3i and minus 3i. And taking the combinations e to the 3it plus e to the minus 3it divided by 2, that's cos 3t, and e to the 3it minus e to the minus 3it over 2i, that's sine 3t. So these are real solutions. Their Wronskian is non-zero at all t, and so we can satisfy any initial conditions. Now, we want to learn now to use the software in order to visualize these solutions. And the software is the second program, and that I've told you to download. It's called Direction Fields, and essentially it solves a system of two first-order equations. You get an equation dx by dt is y. Now let me show you what this has to do with a second-order equation here. Well, the point is, we can always write a second-order equation as a pair of first-order equations by introducing a new variable, a new dependent variable. So, we'll call dy by dt, we'll call that v. Think of y as the displacement in this spring. Then dy by dt is simply the velocity. So, generally speaking, that new variable has the meaning of velocity. In the LRC circuit, our y is Q, the charge on the capacitor. And dq by dt is, of course, what we call I, the current. That's the analog of velocity for the spring. So it's very natural to introduce the velocity. So dy by dt is v. Then dv by dt. Now what is dv by dt? Well, it's d2y by dt squared. But from the equation, d2y by dt squared is minus p dy by dt. So that's minus pv minus qy. So you see, this pair of equations is exactly equivalent to this. If I want to go back from here to here, I just substitute v equals dy by dt, put it in here, and I get back that. Okay? Yes, question? The negatives. You mean this negative? Is that right? Okay. Well, dv by dt is d2y by dt squared. But d2y by dt squared is equal to bringing this and this to the right-hand side, minus them. So you can always write this equation in this form. And this is what we've done here in the program. Except in JODE, our dependent variable is always x, and its derivative, dx by dt, is y. So the x and y in the program corresponds to what we call y and v. The reason we don't always use x is we like to keep x when we were working with first order equations for a possible independent variable. Okay, so the equation we want to put down in the program is dx by dt is y, dy by dt is minus py minus qx. In other words, these equations with y going into x and v going into y. Right. Well, the first example, the first case is dx by dt is y, and dy by dt is minus 4y minus 3x. Okay? So it's minus 4y minus 3x. Notice, to multiply, I put the asterisk in. Now, I'm going to set the time range. I want to start at t equals 0, because I'm going to give initial conditions at t equals 0. Roughly how far do you think I should have to run the thing in time? 1 unit? 10 units? 100 units? What's the solution when I take p equals 4, q equals 3? So we're working on this example. Okay, we're working on this example. So the solution is a linear combination of e to the minus t and e to the minus 3t. So, do I need to go to t equals 100? No, because e to the minus 100 would be ridiculously low. So, roughly 5 is good enough. 5 will take me down to 0. Because we know the solution is eventually going to go to 0, because both parts are decaying. All right, so I choose the range here, 0 to 5. You could choose a 0 to 6 or whatever. You know, you can play a little bit trial and error, but that's the range. And I've chosen the range of x and the range of y to be minus 3 and 3. Okay, so x is, remember, the displacement. So we've pulled it down 3 units or shoved it up 3 units. In both cases, it's going to come back to the middle. But it's going to come back very strongly. It's very strongly damped. So there'll be no oscillations. It'll just come back and stop at the middle. So it's like you've pulled the spring down, but it's very, a lot of friction. So instead of the mass bobbing up and down through the equilibrium point, it'll just go straight back to it. So let's take a look. I always go to the RK4, step size 0.1. At the beginning, I've taken off the slopes. I'll put it back in a minute. This is the solutions. I can put my initial conditions here if I like, or I'll just press the mouse, I'll press the button at where I want to start the motion. All right, so let me start the motion at several different places. Okay, now these tables, by the way, when you put in this data here and here, you press submit all. Then you can choose this, and then when you're ready to go, if you want to clear, you hit clear, and if you want to just submit the calculation, you can do it here, or else just put the mouse on the starting condition. So let's do that. So let's just start, say, here. All right? So I've started at the point x equals 0, y is roughly 2. Let's go over here. Let's start over here. Now let's start on the negative side. It's very interesting. Almost all these initial conditions are ending up coming in along here, aren't they? So they all seem to want to come in along this direction. All right, well, maybe, maybe not. Let's try another one. I'm going to try one. I'm going to start down here. Oh, that seemed to come in a different direction. Now I'm going to do it up here. Oh, so it seems to be if I start anywhere, anywhere out here, in other words, anywhere but along this line, I will come in eventually along this direction, which is the direction 1 minus 1. Now, this is a graph of, this particular graph draws the trajectories. This is y of t, in other words, this is the velocity. This is x of t, the displacement. And as time moves along, the trajectory does this. Okay, in other words, here the y, the velocity, starts out positive, then it ends up going negative, and then back into 0. We can draw what y looks against time. Let's just clear everything. Let's just clear everything here. If we want to draw, here we've drawn y versus x. Now I'm going to draw y versus time. Okay. All right, now we'll start up here at 2. You see, as a function of time, the velocity decreases, actually goes negative, and then comes back here. So in fact, the velocity, it actually did go down. You started with a positive velocity, and then it's, so you were stretching the spring down. Okay, so you're giving it a push in this direction, it went down, and then it turned around, became negative, and came back to 0. Okay, it didn't oscillate at all. If I want to draw the displacement versus time, I change this y to an x. And they're starting at 0. Okay, in other words, this initial condition started the spring at the middle position, but gave it a hit in the positive direction. So I start here, the mass goes down, and then it goes down and then comes back to 0. It doesn't even go through an oscillation. It never gets to the negative x side, because the damping is strong. These situations, these kind of springs are called overdamped. Okay, so now let's go back to the xy picture. So this is y, and down here we're going to put x. In some sense, this has the most information in it. So let's now put in all the curves again. I'm going to start out here with a x of 3 and a y of 4 units. Okay, each unit, by the way, is a half point. So this is like x is 1.5 and y is about 2. But look how they're all coming in along this direction. Except when I go down here, it goes in that direction, and here, this direction. Now, so I'd like to understand this. All right, so it's now you can draw lots of your graphs. Now you'd like to sort of understand what's happening. So let me just take a look. The general solution is the x of t, which is our y, of course. X of t is a e to the minus t plus b e to the minus 3t. What is the y? The y is dx by dt. So y of t is the derivative of him, which is minus a e to the minus t minus 3b e to the minus 3t. Now I'm going to write this in a very nice way. I'm going to write this as a vector, component 1, component 2. Okay, and I'm going to rewrite these in a slightly different way. I'm going to write this as a e to the minus t times 1 minus 1. In other words, the first component is a e to the minus t. The second component is minus a e to the minus t. Then I'm going to write it as plus b e to the minus 3t. And here I'm going to have 1 and a minus 3. So what this is telling us is that the vector, this vector as it moves along here, this is the x of t, this point here is x at the particular time it arrives here, this point is x of t and y of t. And it's a linear combination, you see. It's a linear combination of 1 minus 1 and 1 minus 3. It's a linear combination of that direction and that direction, right? Because you can always write any vector in the plane as a linear combination of any two vectors in the plane as long as they're not collinear, right? As long as they're not collinear. The normal one, the Cartesian, when we say this is x and this is y, we mean x times that direction and the y times that direction. But we can also write it as so much of that vector and so much of that vector. And that's the way the solution comes out. Now, as time goes on, imagine the time is up to 5. Who's bigger, him or him? This guy or this guy? Who's the biggest? This is the biggest. So you see, this guy tends, for large t, to ae to the minus t, 1 minus 1. So in other words, the trajectory after a long time finds its way along here. It comes to here and then comes in the 1 minus 1 direction. Okay? But now, that was the case for most situations, but then when I started here, it just dive-bombed in straight along that direction. What do you think was going on in that case? When I started with the initial conditions 3 or 1 and then minus 3, or in this case the unit's like it's almost 0.5 and minus 1.5, then it went in along the straight line. So yes, what do you expect happened? Yes, now why? Normally, because this dominates this, when does this dominate this? When A is, you see, this tends to this as long as A is not 0. Okay? But what happens if A is 0? Then it'll tend to be e to the minus 3t, 1 minus 3, if A is 0. So you see, there's a very special class of initial conditions for which the A, the coefficient here, turns out to be 0. And they are exactly the initial conditions that lie along that direction. Okay, now in general, in dynamical systems, these are given names. This is called an asymptotically stable fixed point. Okay, we've met asymptotic stability in the context of first order equations. We will put the definitions down soon for second order equations. This guy is an equilibrium point because once you get in there, that's where you stay. And you dive in there as time goes on. But there's two basic directions of approach. This one, where most trajectories will come along, and this very special direction. This one is e to the minus t. This one is e to the minus 3t. So the e to the minus 3t is the strongly stable, they call it manifold. In other words, that's the direction. It's the strongly stable direction. In other words, you go to this one, you know, you get rid of the component in this direction quite quickly, and you end up along the weakly stable manifold, the e to the minus t. They're just words, but you can see the idea. You can see what happens here. So there's more to just than writing down a solution. You want to try and understand it. Any questions? All right, the next thing, let's go to the double root situation. So now I'm going to clear this guy, and I'm going to change the equation to the 4. Now, in this case, we have here, P is 4, Q is 4. The roots are -2 and -2. The corresponding solutions, whose Wronskian is non-zero, is e to the -2t and t to the -2t. Now, in that case, I submit all, and now let's just start things here. And you see, everything will come in. It's very similar to the other case, except it's almost impossible to find the second direction that's connected with the t, because t dominates 1 not very strongly. So mostly you see things coming in along one particular direction. So this is the repeated root case. Again, you have an overdamped situation, no oscillations. The solution, the displacement just comes back into 0. Okay, now we go to a slightly more interesting case. So now we will go to the case where I'm going to take this guy to be 2 and this guy to be 10. Now, what does this mean? If I look at the solutions for r squared plus 2r plus 10 equals 0, then I find r is equal to -1 plus 3i and -1 minus 3i. So the corresponding solutions are e to the minus t cos 3t, e to the minus t sine 3t. So now we submit all here. And now, again, we can leave roughly the ranges and everything the same. Okay, let's clear this. And the first thing I'm going to do is plot y versus t. Okay, and we'll start the thing, say, here. And there we go. So this is the velocity. Let me now start with the x instead. There's the x. So what has happened this time? Okay, here's the spring. We've put the weight on it. It's just hanging there. Okay, I give it an initial condition of a velocity of 2 in this direction, the positive direction. Positive is down in this case. Down it goes. Okay, so x is increasing. X is increasing. It reaches the furthest stretch point. Now it starts coming back. Here it's going through the equilibrium position again, and it goes out the other side. But it doesn't go out the other side as far as it went down the first time because of the damping. And then when it comes back down again, the damping is even less. So it's like as if you have a cosine solution, this solution, but it's sort of as if the top amplitudes decay. Like if you drew a line joining the top of that and the top of this bump here, that would be like the curve e to the minus t. So you get these damped oscillations. And of course, the weaker the damping is, the more wiggles you get before you get things oscillating back to 0. All right, now let's I'll draw the y again. So this is the velocity of the same motion, starting off with an initial velocity downwards of 2, and the initial position is 0, and that's the way the velocity performs. Now if I want to go to the y-x plane, then you can see what happens. I start here, this is the y, this is the velocity axis, this is the displacement axis. So this is the velocity, displacement. So I start off with a big velocity, and the displacement increases till here. Then it starts decreasing again, and the velocity gets negative because the thing is springing back up. Then it's reached the top again, and now it starts to come down again, and so on. And it just keeps on, and eventually it'll stop at the origin if you wait long enough. So, for instance, if I start over at this point, again you go in there. So all these trajectories, they look like spirals winding their way into the origin. Right? Now, let's decrease the damping. So I'll clear everything. I'm going to decrease the damping to 0.2. 0.2. And then I want to have the frequency to be 3 again. So I'm going to make this 9.01. All right? So now if I think I have something wrong there. There we go. Yeah. So 9.01. If the P is 0.2 and the Q is 9.01, then what is this? This is minus P over 2, so that's minus 0.1, so that's minus a tenth, plus I times 9.01 minus 0.2 squared, that's 0.04, divided by 4, 0.01. 9.01 minus 0.01 is 9. The square root of that is 3. So the roots here are minus a tenth plus 3i, minus a tenth minus 3i, giving rise to those two solutions. So now the damping is much weaker. Much weaker. So now let's do y versus t again. Oh, I've submit all. Y versus t. Okay, only we'll do the x versus t first. Okay, we'll start here. Oh, that didn't, because I gave it a 0 y velocity. So let me go back and do the y now here. I'll clear. Let's start here. So now you can see two things. First of all, my range. Now, I've already reached the end of my t range, and there's significant oscillations still. So now it's a good idea perhaps to go back and increase the range of t, because now the damping is like e to the minus t over 10. So to get down to e to the minus, say, 4, which is small, we better go to t equals 40 or something. So we'll take t equals, say, 40 here. Now we'll submit all. And now that's the picture, only I've stretched the time axis to 40 units. Now you can see what happens. This is the velocity. The velocity is high, but each time it goes through an oscillation. So let's look at the position now. So the x versus t. X versus t. So that's what the position looks like. You can see every time, so the thing starts at 0. We gave it a positive velocity, so the pan goes down. Okay, it now turns around and coming back, and it's now at the equilibrium again. Then it goes up this side, and then back and forth. But the oscillations now, the decay of the oscillations is much less. If I draw a graph through the tops of all those maxima, that will in fact look like e to the minus 10. Right? Sorry, e to the minus t over 10. The graph through the tops there. And the underlying wiggle is like the cosine 3t. that okay? Now one more. Let's actually make the damping now 0. 0. And now I'm going to make it exactly 9, because if P is 0 and Q is 9, then the roots are 0 plus 3i, 0 minus 3i, corresponding to the solutions cos 3t and sin 3t. Okay, and now we'll submit all, and here's our solution. In other words, now you're getting the thing going down, up, forever. Now, this is all the other cases, the equilibrium point was 0, 0, right? Because once you got down to 0, 0, the motion stopped. For all the other cases, if you started near 0, in fact, if you started at any values, you went into 0. So it was asymptotically stable, and the basin of attraction, in fact, was the whole xy plane. Now the 0, 0, it's still an equilibrium point. If I make v equals 0 and y equals 0, so that right-hand side is 0, I get dy by dt is 0, dv by dt is 0. In other words, y and v stay there. Or in this language, if y and x are both 0, dx by dt is 0, dy by dt is 0. So that's an equilibrium point. But now, if I start near, I just keep oscillating around it. I stay near. So it's, do you remember the name of that stability? That's Lyapunov stability. If I was working not with a spring, but with a pendulum, I'm down here, I'm just giving it a wiggle, and it's just swinging backwards and forwards in the vicinity where it started. It doesn't end up going away up here or way up here. Now, what's going to be very interesting from the point of view of applications is the following. When we have a circuit or a spring or a pendulum where the damping is very weak and it has these natural oscillations in it, it's going to be very sensitive. It'll react very strongly if you put on a force with the same frequency. By frequency, I'll define it precisely shortly, but by frequency I mean just the same distance between the zeros of this function. Okay? I mean, this is cos 3t and sine 3 is combination of cos and sine. So the zeros occur, like supposing we were looking at cos 3t, its zeros occur at 3t equal pi by 2, 3 pi by 2, 5 pi by 2. So the time interval between the zeros is pi over 3. So that's the time interval, and the period would be 2 pi over 3. From going from here to here, the time interval would be 2 pi over 3. So in other words, in the spring case, the time taken for the thing to go down to the bottom, well, let's start it at the bottom, for it to come all the way back through the equilibrium, out the other side, and then back down, that oscillation would be 2 pi over 3 units. For the pendulum, if I started it here, the time taken to swing backwards and forwards like that, if the corresponding Q was 9 in that case, would be again 2 pi over 3 units. Okay? Now, can you imagine if your force was to just hit this with the same frequency? Well, first of all, supposing it hit it at the wrong frequency. Supposing the force worked like that, I hit it here, and then when it started coming back, I hit it here. Now that would check it. So it's not, the corresponding swinging motion isn't going to have a great amplitude. But now, supposing I'm just hit it in tune like this. You know? This is how you, the child on the swing, you know, you push it, when it comes back, you push it a little more, you don't have to push it very hard, and soon, you know, he's screaming his head off, and he's up in the horizontal position. So this is resonance. We'll define it, you'll see it come out when we solve some equations a little bit later on, but you can get the idea. So if you want to say, if you have a spring-like object, which is weakly damped and has lots of natural frequencies, and you want to break that thing, you don't have to hit it very hard. You just have to get in tune with its natural frequencies. And just make sure you keep hitting those natural frequencies, and the amplitude of the oscillations gets bigger and bigger. And what we're going to find is that basically the resulting amplitude of these oscillations will be like if the initial spring is weakly damped, like R, the resistance in an electric circuit, the response, the amplitude response, will go like 1 over R when you're in tune. When you're not in tune, the amplitude response is much weaker. So this is the way, in fact, that like when we have ozone, the ozone molecule, which is like 3 oxygens tied together with these covalent bonds, they're like springs. The ultraviolet light comes in. The ultraviolet light's frequency is very close to the natural springing frequency of these ozone. If it wasn't very close, it wouldn't get absorbed very much. But because it's close, the response of the ozone is rather dramatic at the frequency of the ultraviolet light, and therefore a lot of that light gets absorbed. Lasers, there's lots of instances in chemistry and in physics in which we use this idea of this resonance. Your radio works this way. How you discriminate between one station and another when you twiddle the knob is essentially twiddling the knob changes the natural frequency of your circuit, the receiver. And you change it so that it matches the frequency of the signal you want to take in, the station you want to listen to. And then the response is very large. The response to all the other stations is very small. So you hear your station and not all the other stations. So this notion, this idea of having natural oscillators like this, okay, and then forcing them in tune with themselves, then you can get tremendous responses. And that'll be very important in many applications. One more thing, I want to show you a very useful way to picture these solutions. For instance, if I have a solution that the displacement is like e to the minus t over 10, and the linear combination a cos 3t plus b sine 3t. Okay? Now the Wronskian between the solution e to the minus t over 10 cos 3t and e to the minus t over 10 sine 3t is non-zero for all time. So I know that this linear combination here, by correct choices of a and b, I can satisfy any initial conditions. X of naught equals whatever I wish to give it, and y of naught, which is dx by dt, given at t equals 0 by the choices of a and b. But then I end up, say, with a equal 3 and b equal 2 or something like that. And now I look at this and I say, well, what does that look like? I know what cos 3t looks like. up and down like that. And I know what sine 3t looks like. It's just pi over 2 out of phase with the cosine. Okay, and I know roughly that the damping, the oscillations will get slightly less large as time goes on. But the composite signal of this and this, in my mind, I find it difficult to add the two together, 3 times cos and 2 times the sine. So now here's a very nice way of rewriting this so that the graph of this signal becomes very clear. I want you to think of your trig formulae. If this were the cosine of something, okay, if this were the cosine of something, and this were the sine of something, then this would be cos 3t cos something, plus sine 3t sine something, and then I'd have cos of 3t minus phi, cos A minus B. But can I find an angle phi whose cosine is this and whose sine is that? Well, imagine A was 3 and B was 2. Can I find an angle, which is real, whose cosine is 3 and whose sine is 2? If you draw the graph of cosine like this, up and down, goes between what and what? What's the range of cosine? Yes? -1 and 1. So I cannot find a phi whose cosine is 3. Any bright ideas? So I'd like something here. I'd like to do something so that whatever's here and whatever's here, if I take his square and add them, I get 1. So how could I manage that? I'd like to do a little finagling on this so that whatever's here and whatever's here, if I square him and add them, I get 1. Divide by what? Very good. What I'd like is for this to be a over square root of a squared plus b squared, cos 3t. And then this is b over the square root of a squared plus b squared sine 3t. Now if I put that in the denominator, I have to put it in the numerator. Now, what is the sum of the squares of this guy and this guy? If I square him and add him, I get well, just do it. Square him, and add 1. And what formula do you know very well in trigonometry? It's Pythagoras' formula. Cos squared plus sine squared is 1. So you see, I can now choose a phi between, say, minus pi and pi, such that cos phi is a over square root of a squared plus b squared. This would be 3 over root 13 if a was 3 and b is 2. And the sine phi, choose it to be b over square root of a squared plus b squared. And if I use those values, this would be 2 over root 13. Okay? Now I can find the unique phi which whose cosine is 3 over root 13 and whose sine is 2 over root 13. So this guy is just cosine phi. This guy is just sine phi. And so I've cos 3t, cos phi, plus sine 3t, sine phi. What does that become? Your favorite subject, right? Trigonometry. So it's just cosine of 3t minus phi. Cosine A minus B is cosine A, cosine B, plus sine A, sine B. Now, that you can picture because you have just an amplitude. You have an amplitude and you have this decay, but the cosine, it's wiggling up and down with period. I mean, it's going up and down with 2 pi over 3 between its, actually it's 2 pi over 3 between successive maxima. And it's phase shifted a little bit. In other words, the place where the cos is, where this argument is 0, so the cos is 1, is instead of being t equals 0, it's t is phi over 3. So you can draw this. This looks like something like this. Right, like that. Where this first 0 might be at phi is roughly, it's roughly, this position here would be t is phi over 3, roughly. Not quite, but because you have to take account of the e to the minus t over 10 bit. Yes?
Under the radicals of the squared?
This one here?
Yeah, but down to the equation.
Oh, it is. Thank you. Thank you, Stephanie. Yep, it's meant to be squared. So this is the amplitude of the motion, this times this, and this is how it oscillates. So writing a cos 3t and b 3 sine t as root a squared plus b squared cos of 3t minus phi is a very useful and very simple device to get a clear picture in your mind as to what the displacement or the charge or whatever you're graphing looks like. Question? Where did I get a equals 3 and b equals 2? I just took that as an example. Okay? It was just if this happened to have been 3 and this happened to be 2, this is the way you write that then as this becomes the square root of 13 times cosine 3t minus phi, where cos phi is that and sine phi is that.
Can you say one more time where you got into the cosine 3t minus phi?
Yeah, by this formula. So the question is, so cosine A minus B is cosine A, cosine B plus sine A, sine B. In our case, A is 3t, this B is phi, this is 3t, this is phi. So cosine 3t cosine phi plus sine 3t sine phi, and that's equal to cosine 3t minus phi. Yes?
How would you use the phi's if you solve for?
Yeah, you'd have to look up your tables. You know it's in the first quadrant. Roughly what would it be? It's the sine is 2 over, it's about 50 degrees.
And then we plug it in.
Yeah, if you want, yeah. But for this course, as long as you tell me what the cosine is and the sine is, you know, you don't have to do the phi unless I ask you where is the first maximum or something like that. Very good.
The damping force, the e to the negative t over 10.
Yeah, that's the damping, yeah. For instance, in the last example, where you'd have a cos 3t and b 3 sine t, then there's no damping. But if the a and B were both, say, 3 and 2, then the net, the composite signal, is a shifted cosine. Right. All right. So now you are comfortable using this. Now I want to go back to our first example and just show you something else. The first example we did was minus, what was it, 4 times y minus 3 times x. All right. And now I'm going to go to y versus x thing again. And because I've given it a wrong initial condition, I'll submit all and clear all. Now I want to go back to this case again. Remember, all the guys... Oh, what have I done? Oh, first of all, I've done 40. I want to just go to 5 here. Now, so clear all. So what am I? Oh, I'm... Thank you. Yes, I'm drawing x versus x, which is quite correct. That's the way it would be. So y, thank you. So now we're coming in these directions. And so this one, like this. And then remember, if you went to the 1 minus 3 initial condition, the very special class of initial conditions that lie along the line y equals minus 3x. Just here. Yeah. Now, I want to show you a neat thing. Remember the solution, the general solution, we express the general point x of t and y of t, say the point out here, as a linear combination of that direction, that vector 1 minus 1, and this vector 1 minus 3. Now, I can write in the plane any vector as a linear combination of 2 other vectors, as long as these 2 other vectors are... Yes, but we haven't reached linearly independent. As long as they're not collinear. So, in other words, the 2 vectors I use as a basis have to have an angle between them. Or if I decide to actually, so this was one direction, this is the 1 minus 1, this is the 1 minus 3. If I decide, say, to complete, think of these as forces, and I'll take the resolvent force, I make a parallelogram like this, and the resolvent force is along here, so much of this and so much of this. I want the area of that parallelogram, or if you like just the triangle, the area of that, in order that they're not collinear, that area has to be non-zero. So roughly speaking, I want, if one of my solutions is y1 of t and its derivative, that vector, and the other one is y2 of t and y2 prime of t. At any particular time, those 2 vectors are sort of the bases. Now, if I have a vector, this vector, and this vector, does anybody remember what's the, if I give you 2 vectors, the area of the triangle that they subtend is proportional to what? Cross product. Exactly. And what is the cross product here? It's y1 of t. Can you guess? Can you guess? Yes, we've met him before. He is the Wronskian of y1 and y2. So basically, the Wronskian being not zero says that the vector I form at any time, I take the displacement y1 of t, and this is one solution like, and his derivative dy1 by dt. I take that vector, and I take this vector, the second solution. And I must make sure that those two vectors are never parallel. They're never collinear. And this is the condition that I need this Wronskian to be non-zero. Now, it's a bit late today to start on this, but what we're going to do next day is we're going to start talking about the Wronskian and the notion of linearly dependent and linearly independent vectors. Only we're going to be talking in terms of functions because they're solutions of differential equations. And what we're going to find is that the Wronskian being non-zero is the same as making sure that the two solutions that you use to build the general solution with, a times y1 plus b times y2, you want these to be linearly independent. But really, it just makes contact with the linear dependence and independence of vectors.